Okay, so today I want to talk a little bit about generative models for 3D data. And in particular, since we are at the AV workshop, we're going to talk about LiDAR data. And especially, how can we repurpose already trained image models to generate also this very different 3D data? So first of all, like why bother, right? So we come a little bit more from the neural simulator side, right? So we want to be able to simulate scenes, to simulate images like multi-view cameras and also LiDAR in like what you would have in an AV stack, so that you can actually test your end-to-end models and see how they perform in this simulation. And of course, like NERF or 3D Gaussian splats are good, but they require like per scene optimization. This is usually slow, and they don't really generalize. And generative models are really like they're really cool, right? I mean, we see them everywhere. We're generating images, we're generating videos, but they only work for these two modalities, right? Like we haven't really seen generation of LiDAR data at scale. And LiDAR is important for safety critical AV. And so in this talk, I'm going to focus mostly on certain research questions. Like the first of all, can we actually learn the distribution of this LiDAR data? Can our generative models generate this type of data? Can the video priors that we help in our image models, in our video models, help with LiDAR generation? And finally, kind of the holy grail, right? What we want to do is we want to jointly model RGB images and LiDAR data. So let's see how to do that. So I'm going to start with the NVIDIA Cosmos Foundation model. So some of you might know that it was released a few months ago. It's basically like this video generative model, and it has been customized for physical AI setups, and we know it works well for AV. I will show some images later. And it has like two ingredients, which I'm going to focus on because these are the ingredients that we're going to need to change in order to generate also LiDAR. So the idea would be to repurpose this model. Of course, like the first thing that we're looking at is the video tokenizer, right? I mean, we have completely different modalities, so we're going to have to change our video tokenizer into a LiDAR tokenizer. And then we have the DAT-based diffusion model, which is depicted in green. And I'm going to basically explain like how do we put our prompts, how do we put our conditions in order to generate data that, for example, follow the information of a map or the information of the RGB image. Okay, so we already know that this foundation model can generate AV data, right? So here we input, for example, LiDAR and HD map. So the HD map is the second image. It's kind of represented by different colors. Like, for example, the lane lines are one color, the bounding boxes for the cars are another color. And then we have the caption at the bottom. And this is the generated output that we actually have. And this is already like embedded in this model, right? So this model knows already AV data. So this is already a good starting point. It can already generate multiple views. So for example, here we see the same scene that we want to generate in New York. And in the bottom, in this kind of like sakura, so you see like all these flowers that are falling. And you can see that the views are actually pretty consistent, right? So this is already something that the model can do. So it's a pretty good starting point for AV. And so the question is, okay, let's do enough for LiDAR, right? I mean, the starting point is good, the domain is there, but we need to think about some things. Like the first one is the representation. What kind of representation are we going to use for LiDAR data? Where's the tokenizer for LiDAR? Do we need to retrain it? Can we reuse the video tokenizer? What are the conditions that we can use for LiDAR generator? Can we, for example, generate from map information, from RGB, and how to jointly model LiDAR and RGB? So, okay, let's talk about the representation. So we have like pretty different representations if we think about repurposing an image or video model, and we think about LiDAR, which is basically like a non-structured point cloud. There's obviously like too much of a difference in there. And so what we do is we follow a more structured representation. So we convert LiDAR into range map. so that we can basically effectively reuse all the infra that we built for image generation, right? So this is just a question of how to make things easier for us so that we don't need to retrain everything from scratch. Now let's go to the tokenizer. So the first thing that we tried was, of course, like, let's just try the image tokenizer, applied it to LiDAR range. And basically here, like, we have the input, and in blue we have the reconstruction, and you see that it's pretty bad, to be honest. So this was our starting point, right? We say without retraining anything, this is what we obtain. It's very noisy. It sometimes doesn't even follow the structure of the road. So the question is, how can we improve on this initial result? Now, there's several things that one needs to do to get a good tokenizer for LiDAR data, and I'm just going to mention 3 aspects. So first of all, you kind of have to understand what a tokenizer is about, right? So a tokenizer is about compression. So you have to be smart about the redundancy of your data. So if you look at the range maps, there are these kind of long image representations. So you have a lot of dense information in the columns, but the rows are something that you cannot really compress, right? So what we did was we basically applied a 4 row repeat. So we stack the range images one on top of the other. And this changes things a lot, right? Because now you're not compressing the raw information so much, and so you're keeping more of the structure of the LiDAR data. You also need to accurately model your sensor, right? So you need to understand your sensor. You need to handle, for example, motion compensation. So you see here how we were training things in the top image, where you see the same structure, which is in completely different positions in the range map. And when you undo motion compensation, then you get the aligned structure. So this is something that you need to take care of, and you need to know how your sensor behaves. And then another thing is model precision really matters for depth estimation, right? So the tokenizer that was used for images used BF16. And if you look here at the map of the depth, you can see that we have up to 5 centimeter inaccuracies just by using that precision. So this is something that we could not live with. So we had to use FP32 to fine tune the tokenizer while still keeping the diffusion model at BF16. So these are just like 3 ingredients, which are it's kind of technical. It's kind of like these small decisions, but they do make a huge difference. So this is how now the tokenizer looks like, right? I mean, we're just trying to reconstruct the data here, and you see the huge difference that we had from before, right? So now the structures are much more precise, like even the road is straight. The cars are also much better depicted. There's much less noise in general. And this just comes from these 3 changes that I've mentioned. Okay, so let's see what we can do with that. Let's have some fun with that. So the first thing that we can do is try to condition our generation, right? I mean, in the end, we want to generate scenes that we're interested in. And one of the conditions that we can use is using basically HD map and bounding boxes. So with this, you're basically fixing all the layout of the scene, right? You're saying how the cars are going to move around you. You're saying how the road is going to look like. And then you can change things like, the weather or the buildings, things like this. And we're going to create basically the same representation that we have for LiDAR. We're going to create the same representation for HD maps. So you see here like all the bounding boxes flying around. You see the lanes being marked, traffic signs, things like this. Another thing that we can use as condition is, of course, caption, right? And this is very useful to change weather conditions. So here you can model a rainy day LiDAR, and at the bottom you can model it on a normal day. And you can see really the effects of the rainy day, where you just are dropping rays everywhere, right? A classic characteristic of rainy sequences. So, okay, how do we actually control HD map generation? So we're going to have, this is going to be like single LiDAR frame generation, and it's going to be applied later to the LiDAR sequence generation, and it's going to be exactly the same, basically, for image and for video. And what we're going to do is we're going to input into our DAT diffusion model, we're going to input our noisy LiDAR tokens that then we're gonna denoise. And when we're going to input, we're going to basically concatenate clean input condition tokens, in our case, HD map, right? So the noisy ones are the LiDAR. This is the ones that we're going to denoise. And in the HD map are clean tokens. And so these are the kind of things that we can generate. So here we have at the top the reference LiDAR, the generated LiDAR, and the condition that we have. And you can see that it's not super easy to see, but some of the objects that are being placed in this condition are actually placed appropriately in the LiDAR map. And also the road structure is the same. So here I'm always showing in blue the generated LiDAR and in yellow the reference, but here we're not doing reconstruction, right? So I just show the reference so that you can see the quality of the LiDAR and you can kind of compare if this quality makes sense with respect to the generated output that we have. Here's another example where we can see two pedestrians. So I think this is really cool, right? It's a scene full of pedestrians. And you can see the pedestrians that are being nicely generated here, even with, shadows and stuff like this. So I think the detail that we get with these generations is actually pretty awesome. Now the weather control, right? I said that we wanted to do weather control. So here what we're going to have is we're going to have the HD map condition, and we're going to have the caption, which is going to control whether we generate a sunny sequence, which is what we get on the right, or a rainy sequence, which is what we get on the left. And again, here we can see like all the rays dropped in the rainy sequences, which is a typical effect that we have for LiDAR data. Yeah, another sequence with another image. So this is, again, single LiDAR generation. And now we go into the video model, right? So the video model is a little bit more complex, but essentially you're going to condition the thing in the exact same way. And you can see here the condition that you have, right? Like you have all the road structure, we have the cars. And this is the kind of sequences that we started generating. So you can see that it really follows the structure. It really follows the objects. It's a little bit more noisy than the image model. And now let's go into what we actually want to do, right? I mean, we want to model the full stack, right? I mean, we want to model the LiDAR as well as the RGB, and we want this to be paired, right? We want the information to be paired between what we're looking in the multi-view cameras and what we're looking in the LiDAR space. And so how we're going to do this is essentially we're going to have our noisy LiDAR tokens, which are infused into the diffusion model, which are going to be denoised. We're going to have the noisy image tokens, which are going to be denoised. And we're going to have our HD map condition, same as before. This is clean. This is not noise. And we're going to have some view embeddings, right? Because you want to be able to tell the model to generate different views, and you want to be able to encode these different views. So you can think about this as, you have one view, which is the LiDAR, and all the other views are the images. You can also think about it this way. And we have one model for both. So this is important, right? We don't have a diffusion model for LiDAR and a diffusion model for RGB, but we have a single model for both. And now we can see the kind of things that we can generate, right? Like this is the reference image, this is the generated image, and the condition with all the road structure and the bounding boxes. And one thing that we wanted to check, right, was how does it align, right? Like how does LiDAR align with RGB? We want to be able to show that we have the same structure in the same 3D position. Otherwise, any model that you train is not going to be accurate, right? Because it's not going to have the right information at the start. So here what we do is we basically project the LiDAR into the images, and we see that it follows the structures pretty nicely. So this is the generated output, and we see this is a straight road. It's generating the straight road. There are some cars also parked, which are also being generated. And here's another projection where we have a bridge. So this is pretty cool because there are not many bridges in the data. But still it's able to capture the structure of the bridge, and you can also see the LiDAR points here that are being correctly projected on the bridge. And also you can see the structure here in the LiDAR data. So that's also pretty cool that we can generate data that we haven't seen so many examples of. What happens if we want to do a different thing? We want to, instead of condition on the HD map, we want to condition on the RGB images, right? So we have plenty of stacks that just have multi-view images and they don't have LiDAR. What if we actually want to enrich those stacks with LiDAR so that then we can train, we can measure for, safety measures, explainability, things like that. And so this is also something we can do, right? In that sense, you don't put as a clean input the HD map, but you put your image as a clean input and your LiDAR as a noisy input. And then you just denoise the LiDAR part. And this is what you get. Also, like very, very good alignment between RGB and LiDAR images. So this is basically an RGB image to LiDAR, 6-camera model. So we get like the 6 cameras as input, and we generate the LiDAR as output. And we see like all the cars are correctly generated in the LiDAR space. The alignment is actually pretty good across all the cameras, and the 3D structure also looks really nice. Okay, so just for some final thoughts. So we started with the results of this tokenizer, which were actually quite bad. By putting some effort into understanding the sensor, understanding the noise in the data, understanding what a tokenizer actually does and what information we want compressed and what information we don't want compressed, we could get to a nice generative model that generates much more crisp LiDAR, where we can observe cars like very nicely. We can observe like even pedestrians, like thin structures are properly generated. And this was done by post-training the Cosmos-based model for LiDAR generation. So all the nice video properties and priors that the model has are built into the LiDAR model. And there's actually pretty decent alignment between the two modalities. I think this is something that we can improve on. But basically the main objects, the main structures are really nicely aligned. And so, yeah, with this, I will open the floor for questions, and thank you for your attention.